In Fermi-Dirac statistics, you have seen in the first lecture on this subject the famous distribution law of Fermi-Dirac. Now, from today, we are going to start to deal with the different applications of Fermi-Dirac statistics. Okay. Actually, Sommerfeld, a well-known scientist, proposed free electron theory of metals. And this free electron theory of metals proposed by Sommerfeld finds use of Fermi-Dirac statistics variously. There are so many applications of Sommerfeld theory, and all those applications will be called application of Fermi-Dirac statistics because Sommerfeld developed his theory by the use of Fermi-Dirac statistics. Okay. The first and foremost application which we will see in this regard is to find or to calculate the electronic specific heat. But before the calculation of electronic specific heat, we will also have to see some of the simple applications of Fermi-Dirac statistics, and those are actually the calculation of density of states and Fermi energy. Actually, this subject is studied both in statistical mechanics and in solid state physics. So you can say that these videos are not only of statistical mechanics purpose, but it is equally important for the discussion of solid state physics, particularly Sommerfeld's free electron model of metals. Okay. So now let us discuss in this first application the calculation of density of states. Okay. So we will start this application by using the Sommerfeld's theory of free electron for metals. Actually, in Sommerfeld theory, Sommerfeld assumed that particularly the valence electrons are loosely bonded to the nuclei, and so they are almost free, and so they are called free electrons because they are loosely bonded. Okay. Now, these electrons were assumed by Sommerfeld to be confined inside a cubical box of potential. He assumed that there is a potential box of cubical shape whose each edge is L, and the free electron is confined within that potential box. Okay. In fact, his assumption was that inside the potential box, the potential energy function, or you can simply say potential function, is equal to 0 everywhere inside the box. Okay. But outside of this box, the potential is infinity. So the electron confined within the box cannot surmount, cannot penetrate through the wall of the box and move to outside. So the electron is completely confined within the box. Okay. Then Sommerfeld applied the time-independent Schrodinger equation, solved it, and for a single electron, he calculated the energy eigenvalue and the eigenfunction for the electron. Actually, this subject has been completely dealt in detail in my lecture on quantum mechanics, so you can see the problem of three-dimensional potential box in my playlist of quantum mechanics. Okay. Here I have actually mentioned the important results for this. As you can see that if you talk about a single particle or a single electron inside the potential box, the Hamiltonian of that particle will be what? The single particle Hamiltonian is minus h bar square over 2m del square plus V of x, y, z. And when you will write Schrodinger equation, that is H psi equal to E psi, and we solve this equation, we will get the energy eigenvalue and eigenfunction of this Hamiltonian operator. As I have told you that this potential function V of x, y, z, this is 0 inside the box. So you can say that V of x, y, z is 0 when x lies between 0 and L, y also lies between 0 and L, and z also lies between 0 and L. But it is infinity if the situation is not like that. Okay? When this Schrodinger equation is solved, as I have told you, you can consult my video in quantum mechanics, then you will find that the eigenfunctions of the Hamiltonian are given like this. This is psi nx, ny, nz of x, y, z equal to root over 8 by L cube sin nx pi x by L times sin ny pi y by L times sin nz pi z by L. Actually here these nx, ny, nz are quantum numbers. No, these are in fact equal to 1, 2, 3, 4 and so on. Okay? The energy eigenvalue obtained after the solution of Schrodinger equation is like this. This is E of n, E nx, ny, nz equal to pi square h bar square over 2 ml square nx square plus ny square plus nz square. Okay? Now, as these nx, ny, nz has discrete value, so you can say that the energy eigenvalues are discrete. Okay? Discrete. And if you try to find what will be the energy eigenvalue for the quantum numbers nx equal to 1, ny equal to 1 and nz equal to 1. You can see from this equation B that this energy eigenvalue E111 is equal to 3 pi square h bar square over 2 ml square. Okay? Now, a particular set of these quantum numbers nx, ny, nz represent a quantum state. Okay? So this 1, 1, 1 represent a particular quantum state, and for this energy eigenvalue, you can see there is only one quantum state. So we say that the energy eigenvalue E111 is non-degenerate. Okay? It is non-degenerate. Okay? But now let us consider three eigenstates defined by the quantum numbers 112, 121 and 211. All these three set of quantum numbers represent the three different eigenstates or three different eigenfunctions or three different quantum states. But when you will find the energy eigenvalue for any set of these quantum numbers, that will be same, and you can see that these energy eigenvalues are given like 5 pi square h bar square over 2 ml square. So you can see that for this energy eigenvalue there are three quantum states, and so this energy eigenvalue is called threefold degenerate, or the degeneracy of this energy eigenvalue or this energy level is actually 3. Okay? Corresponding to this, there will be three quantum states of our system. Okay? And similarly, you can find the degeneracy of other energy eigenvalue too. Okay? In fact, apart from this degeneracy, there are some accidental degeneracy too. Okay? Now, you can see that according to equation B, the energy eigenvalue is discrete, and so we say that this is the quantum feature of the electron because the energy eigenvalues are not continuous. But what happens in practice? Actually, in practice or in actual state of affairs, it is found that the different energy levels are not far separated. They are so close to one another that you can consider that the energy eigenvalues are almost continuous, or the energy levels are not discrete but continuous. So instead of saying that EI is the energy of Ni particle, we talk about an energy range. We say that this N of E represents the number of electrons or number of fermions or number of particles in the energy range between E and E plus dE. We do not write the leveling of this energy level, but we talk about an energy range. If this energy range dE is very small, this number you can think will be also small, and this N of E dE will then represent the number of electrons or fermions having energy between E and E plus dE. Okay. Now, as I have told you earlier that in this short lecture our aim is to find the expression for density of states. But you have learnt about the occupation probability or Fermi-Dirac distribution function in the earlier lecture, and you have seen that this Fermi-Dirac distribution function is denoted by the symbol f of E, and actually this f of E is the measure of probability of finding the fermion in energy level E. It means what is the probability of finding of a fermion in finding energy level E? That is measured by this occupation probability. Okay. So this f of E is actually defined as the number of fermions per quantum state at energy E. This is number of fermions per quantum state at energy E. It means what is the average number of fermion in one quantum state. That is measured in terms of this distribution function, which is called Fermi-Dirac distribution function. Okay. And when you talk about the density of states, you have already studied in very detail this density of states while the study of Bose-Einstein statistics. The definition is same, but expression will be different because our statistics has been changed. So you can remember, you have learnt that density of states, which is denoted by the symbol G of E dE, that actually represents the number of quantum states in the energy range between E and E plus dE. Okay. So if you have to find the expression for this density of states G of E dE, you have to find what will be the number of quantum states present in the energy range between E and E plus dE. Actually Sommerfeld utilized the semi-quantum mechanical theory. In one hand, he assumed phase space, which is purely a classical concept. On the other hand, he also assumed the spin of the electron, and the spin, you know, is purely a quantum mechanical property. So this Sommerfeld theory is also called semi-classical theory, or you can say semi-quantum mechanical theory, because in the development of this theory, both of the concepts are used. Okay. Actually, to get the number of quantum states in a given energy range, we have to find what is the volume in phase space in that energy range. When you will be able to find the volume, which is also called hypervolume, in a particular energy range in phase space, you can easily find what will be the total number of quantum states in that energy range. So let us try to find the volume in the phase space corresponding to the energy between E and E plus dE. Okay. Now, as we have defined that this distribution function is actually the average number of fermions per quantum state. But let us see. If you consider that this G of E dE is the number of quantum states in energy range between E and E plus dE, and this N of E dE represents the number of fermions present in that energy range. So N of E dE fermions are present in the quantum state G of E dE. in this number of quantum state, the number of fermion present is n of E d. So one fermion will be content in how many quantum states? That will be G of E dE. Sorry, this is just reverse. You have to say that in G of E dE quantum state, the number of fermions present is n of E dE. Okay? So on average, in one quantum state, what will be the number of fermions? That will be n of E dE divided by G of E dE. Okay? And as you know that the average number of fermion per quantum state is called Fermi-Dirac distribution function, or the occupation probability. So you can say that this occupation probability f of E is equal to what? This is n of E dE divided by G of E dE. And so you can say that this n of E dE is equal to G of E dE times f of E. Okay? Here you know that this f of E, which is called occupation probability or Fermi-Dirac distribution function, you have already obtained the expression for this f of E in the previous lecture. So you can remember that this f of E is equal to what? This is 1 over 1 plus e to the power E minus EF divided by kT. This is expression for the occupation probability. You know that this EF is known as Fermi energy or Fermi energy level. And what is this Fermi energy level? Actually, we will calculate this Fermi energy level in the forthcoming lecture. But till now, you have to know that this Fermi energy represents the maximum energy of fermion at 0 Kelvin temperature. Okay? Actually, you know from classical physics, when you talk about energy at 0 Kelvin, that is simply 0. But quantum mechanics says that even at 0 Kelvin temperature, energy will be not 0. So the energy possessed by a fermion at 0 Kelvin, maximum energy possessed by, not energy, but maximum energy possessed by a fermion at 0 Kelvin temperature, at absolute temperature, absolute 0 temperature, that is called Fermi energy. Okay? So this is also called the highest occupied energy level at absolute 0 temperature. Okay? And K is the well-known Boltzmann constant and T is absolute temperature. Okay? Now, as I have told you that in Sommerfeld theory, electrons are treated free. Free means free from potential, free from force. And if you are talking about a free particle, you know, a free particle has no potential energy. We simply take its potential energy 0. So in case of a free particle, when you talk about the total energy, that means kinetic energy. Okay? So as in Sommerfeld's theory, electrons are treated non-interacting. So you can say that energy of electron is simply its kinetic energy, and so you can write that E is equal to P square over 2m, where P, you know, is the linear momentum of our electron. And so that you can say that this P is equal to a square root of 2m. Okay? Now, it is clear from this result that this magnitude of momentum P of the electron is directly related to the energy of electron. So you can think that when energy of the electron is E, we can assume that momentum of the electron is P. And when energy is E plus dE, then you can say that momentum of the electron is P plus dP. Okay? So when you talk about the energy between E and E plus dE, that fact is same as you are saying that momentum is between P and P plus dP. Okay? So the number of quantum states between energy E and E plus dE and number of quantum states between momentum P and P plus dP, both will be same. So this density of states, which is denoted by the symbol G of E dE, that can also be denoted by the symbol G of P dP, and both will be same. Okay? And so you can say that this g of p dp is nothing. This is simply the number of quantum states in the momentum range between p and p plus dp, and that will be simply equal to the number of quantum states in the energy range between E and E plus D. Okay. Now, for getting the value of this density of a state, as I have told you earlier, you have to find the volume in phase space for energy between E and E plus dE, or momentum between P and P plus dP. Okay. You know that the volume in phase space is simply a product of the volume in position space and volume in momentum space. Okay, so you can write that volume in phase space corresponding to the energy between E and E plus dE, that will be equal to volume corresponding to the momentum between P and P plus dP, and that will be equal to volume in position space. That volume is given by integral of dx, dy, dz, and volume in momentum space is given by integral of dpx, dpy, dpz. Okay, I have not written here any limits, but when the actual problem will be solved, there must be proper limits. Okay. Now, as you know that we have assumed our particle, that is electron, is confined within a potential box which is of cubical shape of size L. So this volume of geometrical space, or you can say position space, that is integral of dx, dy, dz, this is simply equal to L cube. This is volume of the potential box, and we write this L cube as V. In our calculation, instead of L cube, we will write V. Okay. Now, the volume in momentum space, what will be the volume in momentum space corresponding to this energy range or momentum range? This is denoted by integral of dpx, dpy, dpz. And you know, this volume is simply the volume between two concentric spherical cells of radius p and p plus dp. Okay. In momentum space, if you consider two spherical cells whose center are same and their radii are p and p plus dp in momentum space, then the volume enclosed between these two spherical cells, which I am showing here by this shaded region, that represents actually this volume. And you know, this volume will be equal to 4 pi p square dp. You can think that 4 pi p square is the surface area of this sphere of radius p, and when you will multiply that 4 pi p square by the thickness dp, you will get the volume. Okay, so this integral is simply equal to 4 pi p square dp. Okay, now you have calculated the volume in position space and volume in momentum space, so you can say that the volume in phase space corresponding to the momentum between P and P plus dP, or energy between E and E plus dE, if it is denoted by d gamma, this will be equal to V times 4 pi p square dP. Now, we can change the parameter P and use E, because P and E are related. You can see, you have seen earlier that this P is equal to a square root of 2m. So when you will find this dP, that dP will be a square root of m by 2e dE. So instead of this dP, you can write a square root of m by 2e dE, and at the place of p square you can write 2m. So after substituting these, you can get the value of this d gamma, and this is 4 root 2 pi v m to the power 3 by 2 e to the power half dE. Okay. This is volume in phase space corresponding to the energy between E and E plus D. Now, you have studied at various places that H cube volume, where H is Planck's constant, H cube volume corresponds to one quantum state, Qs for quantum state. So, you can say that in H cube volume, the number of quantum state is 1. So in unit volume, the number of quantum state will be 1 by h cube. So what will be the number of quantum states in d gamma volume? That will be d gamma divided by h cube. Okay. So, and number of quantum states in the phase space in volume d gamma, which is volume corresponding to the energy between E and E plus D, that is called density of states. So you can say that this density of a state G of E dE, this is equal to d gamma over h cube. Now let us substitute the value of d gamma. This is 2 pi v 2m to the power 3 by 2 e to the power half dE divided by h cube. Okay. So this is the value of the density of a state. But till now we have not considered the spin of electron under account. Okay. This result is valid for the Maxwellian particle or the classical particle where spin plays any role. But here our particle is electron, which is a fermion, and you know that electron has two spin states. It may have up spin or down spin. So when you will take the spin of the electron under account, then the number of quantum states in this energy range will be just double of this, because there are two spin states. So corresponding to a given quantum state, there will be two spin states, and both spin states represent the different quantum states. So the actual value of density of states will be twice of this value, and so you can write that when we will take the spin of the electron under account, that will then the density of a state G of E dE will be equal to 2 times of that much value. And so you can write that this G of E dE 2 into 2 pi v 2m over h squared to the power 3 by 2 e to the power half dE. Now for this factor 4 pi v times 2m over h square whole to the power 3 by 2, I have written here C. Okay. So that this result can be easily remembered, but you must remember the value of this C. So finally we get that the density of a state G of E dE is equal to C times e to the power half dE, and you can see that this density of a state is proportional to a square root of energy of the electron. Okay, and must remember the value of C. So we have calculated the density of states by taking the spin of electron under account, and so this theory in this theory we have utilized both the classical concept of phase space and the spin concept of electron, which is a pure quantum mechanical concept. Now in the forthcoming lecture, utilizing this expression of density of states, we will see what is Fermi energy and what is the expression for Fermi energy and what are its different characteristics. Okay, thank you very much.